Hi everyone. In the last session, we have seen DC motor performance equations. So in today's class, we will see the speed control of DC motors. According to the basic equation, that is omega m is equal to Eb by pi, which is equal to V minus IaRa by pi. As per this equation, the speed can be controlled by using these three variables. Speed omega m is controlled by using three variables, that is voltage, armature resistance and field flux. That's why there are three methods. One is armature voltage control method, field flux control method and armature resistance control method. We'll see one by one. First one is armature voltage control method. So it is preferred because of its high efficiency and good transient response and good speed regulation. So in this method, the speeds can be controlled below the rated speed or below the base speed, because the armature voltage cannot be allowed beyond its rated value. If you go beyond its rated value, there is a chances of insulation failure. That's why we need to set the voltage below the rated voltage. So we cannot go beyond its rated voltage. That's why armature voltage control method is applicable for below the rated speed. So if you see the speed torque characteristics of this armature voltage control method, for separately excited motor, for separately excited DC motor, field flux is constant. So field flux is constant and speed versus torque characteristics are almost constant, because we'll keep the supply voltage as constant. Then the drop across armature resistance is almost zero, so it is almost constant, or the characteristics you will get it like drooping characteristics. If we consider the armature resistance, there is a slight droop in the characteristics which shows with the dotted line. And for the natural characteristics are at rated voltage, the characteristics are the above line or first line. When you are decreasing the voltage beyond its rated voltage, VR is greater than V1 is greater than V2. When you are reducing the voltage, correspondingly the characteristics will shift downward. Initially, if we set the voltage at some 200 volts, the characteristics will be at rated voltage VR. If it is 180, the characteristics will shift downward. If it is 160, the characteristics will shift further downward. Likewise, the characteristics will shift downward when you are decreasing the voltage. In a similar way, the speed torque characteristics of the series motor are shown in this figure. Like speed torque characteristics, natural speed torque characteristics are like this, which are with the rated voltage. When you are decreasing the voltage, VR is greater than V1 and V1 is greater than V2. That means V2 is less than V1 and V1 is less than VR. When you are decreasing the voltage level, as speed is directly proportional to the voltage, by keeping this flux as constant, your characteristics will shift downward. So this is all about the armature voltage control method and the speed and its speed torque characteristics. And if you see the field flux control method, the field flux control method is used to control the speeds above its base speed. Above its base speed. The maximum speed by using this speed control method is, or allowable speed is, up to its twice the rated speed above the base speed, but there is a limitation, that is we can go up to twice of its rated speed. And in specially designed machine, it can be up to 6 times of its rated speed. Specially designed machines, generally we can run with more RPM. So in separately excited motor as well as the series motor, we'll see the speed torque characteristics. If we see the speed torque characteristics in the separately excited DC motor, by keeping the flux as constant. In separately excited motor, flux can be constant, and by varying the voltage across the field winding, we can keep the flux as constant. We can set some voltage across the flux to keep that flux as constant. Okay, then if we see here speed versus torque characteristics in flux control method, we'll keep the voltage as constant and we need to adjust the field flux to get the different flux as it is flux control method. In the natural speed torque characteristics for the separately excited DC motor, it is almost constant speed torque characteristics like this with the rated flux. And here we need to control the, and this is natural speed or base speed. Here we need to control the speeds above its rated speed. That's why we need to decrease the flux. Pi rated is greater than pi 1 is greater than pi 2. That means further we are reducing the flux to get the above rated speed, because speed is inversely proportional to the flux. In the base speed equation, omega m is equal to V minus Ia Ra by pi. There we are keeping the voltage as constant and we are controlling the flux. Omega m is inversely proportional to the flux, means by decreasing the flux your speed will increase. So that's why you are decreasing the flux. Here pi r and pi 1 is less than pi r, pi 2 is further less than pi r as well as pi 1. That's why the characteristics are shift upward, that is above the base speed. And in a similar way for series motor, these are the natural characteristics pi r with rated flux, and when you are decreasing the flux, that is pi 1 is less than pi r, pi 2 is less than pi r as well as pi 1. When you are decreasing the flux, as speed is inversely proportional to the flux, your characteristics will shift upward like this. That's why you are getting the above rated speeds. So this is for field flux control method. And the last one is armature resistance control method. In the armature resistance control method, we need to control the armature resistance. What is the equation? That equation is omega m is equal to V minus Ia Ra by pi. So here Ia Ra drop is there. The speed is varying by wasting the power in external resistance that are connected in series with the armature. In series with the armature, we'll connect one resistance. By wasting the power in that resistance, your speed is going to be controlled. The speed torque, natural speed torque characteristics are same. Again, in the separately excited motor, this is the constant characteristics. Those are the natural characteristics. Like I told you, in the separately excited motor with armature voltage control method, there is a slight droop in the characteristics, because we are by neglecting this armature resistance drop, your characteristics will be constant. But if you are considering this armature resistance and you are controlling this armature resistance, as you are increasing this armature resistance, the gap between the natural characteristics and new characteristics will be more. So as you are increasing the armature resistance, these characteristics will shift downward like this. Initially the characteristics will start at the same point, because as per this equation, armature resistance control method, the IaRa drop, as IaRa drop is increasing, IaRa drop is increasing, your speed will reduce, because V minus IaRa, right? This drop is increasing means overall numerator will decrease. That will decrease the speed of the motor. So that's what it shows here. In a similar way, in series motor also, as you are decreasing the armature resistance, these are the natural characteristics. The above characteristics or first characteristics are the natural characteristics with the normal armature resistance at 0.1 or 0.2 armature resistance or 0.5 ohms of armature resistance. But as you are increasing the armature resistance, your numerator will decrease, that will shift the characteristics downward. Because omega m will decrease, that will shift the characteristics downward as the armature resistance is increasing. In this way the characteristics will shift. Okay, so this is inefficient method because we are wasting the power in the armature resistance. So that's why it is inefficient method, and in practical we don't use this method because we are wasting the power. However, in few applications like intermittent load applications, where the load or the duration of the speed control is limited, for example in the traction intermediate load applications, in the traction we need to control the speed frequently during the frequent intervals, start and stop. So in that applications we can go for this armature resistance control method. However, the same thing can be achieved by using the armature voltage control method also. That's why this method can be replaced by the armature voltage control method.